Welcome on board Regina Alaska. I've come to the Azores. It's fantastic. I had a great passage from La Coruña to these mid-Atlantic islands. I've been to Peter's Cafe Sport, met some great sailing pals there, had my gin and tonic, and it's really the origin of the Atlantic. People come from everywhere, from all over the place around the Atlantic, and they meet here. So it's always a reason to cross at least half an ocean to get here. Many people, they just use a GPS or electronic navigation, and that's fine. But I'd like to pass on some ideas why you possibly should not 100% rely on your electronic navigation. And besides, maybe you're one of them who already own a sextant but don't know how to use it. Yes, I have a 10 hours plus video course on the internet, so you can do the whole thing, all planets, all stars, all twilight calculations, even the moon, which is so impractical to use. Or I invite you to go to join one of my Yachtmaster Ocean theory courses in Malta. 6 days, we have so much fun. It's so much more than just celestial navigation. We talk about weather and route planning. We dream along, and in the evenings we go out eating and continue to dream and talk about boats and equipment and stuff. It's just a great comradeship. But maybe you are not in Europe. Maybe you just want to use your sextant, get to know it, and that's why I got this question. Leon, can't you just do a shorter version of a celestial course? I don't want to know it all. I just want to use my sextant. What I would like to encourage you is maybe to dip a bit deeper into the science and get to the pinnacle of seamanship, to try out celestial navigation. It does seem a bit complicated, and the course that I have put together here now is in several parts. It is some theory which you're looking at now, which you're going to watch when I stop talking here. Then a hands-on sight reduction, sun-run sun on the passage from Spain to here, the Azores, a couple of weeks ago now. And so you can grasp it maybe. And the more you do it, the more you get behind the idea and the more you understand it. Well, I hope this helps you to just get out, have fun, use your sextant, and grow a little bit more as a seaman. Have fun watching, and contact me if you'd like to go one of my celestial courses. During this shortcut celestial navigation course, I don't want to convince you to use the sextant instead of the GPS. No, this is a short summary just to give you an insight of how it's being used. Dig out your sextant and just go out and use it, because it's really become a revival. There are so many people who love to learn how the ancient sailors have been navigating for hundreds of years. Even the US Navy has to learn it again. Even they don't trust the new GPS system any longer, so to speak. And besides, the RYA and the MCA, they require it for any ocean sailing. The interesting part is that 3,500 new sextants are being sold every year, in addition to all the old ones that are still around. And only 3,000 RYA Yachtmaster offshores are being examined every year, and they don't even need to know the sextant. And no more than 300 Yachtmaster Oceans are being examined every year. So all the other sextants, how are they being used? Or are they maybe not being used and it is postponed how to learn it? Just take this short course and see the background and how you can use it in on a daily basis, really. Personally, I think you shouldn't leave shore without a sextant, because it's a good backup system. Since today's electronic navigation, well, you can question if with internet and GPS it's still necessary to use anything but electronic navigation. Is this classic navigation still feasible? Well, I can say yes, because you have the lightning strike, and a lightning strike can be quite devastating. Well, first of all, the lightning goes the shortest way from the mast into the water. And if you don't have a lightning protection built in, it may jump from the shrouds through the GRP into the sea. And this can even sink the boat. So the first thing that you should be doing is to build a lightning protection. That at least prevents sinking. So you take all the shrouds and all the stays and the mast and connect it to a keel bolt. If you're not happy enough or lucky enough to have a steel or aluminium boat, that is. You need a little spark distance so that you don't get galvanic corrosion. But it's good to have this connection. It doesn't have to be all the shrouds and stays. If you only connect the mast, you've come a long way. So the lightning can go through the mast via the spark distance into the keel bolt, because the lightning is so high voltage, so it doesn't even notice the spark distance. But for galvanic corrosion, it's good to have this so you don't have some DC current running around in your boat. And even if you're not directly hit, you can have an indirect hit. That means that the lightning is striking another boat in a marina next by, or in the water close to your own boat. The good thing with a sailing boat is that you are protected in such a cone, because in this cone the lightning would go into the mast and not strike you on the foredeck, for instance. This is not the case with powerboats because they don't have a mast, so it could actually be a direct hit for your body on a powerboat if you are on foredeck or aft deck. So let's say that you are protected. You will not sink because you have a lightning protection system on board by just connecting the mast with a keel bolt, and you're not going to be killed because you have a mast. How about the electronics and the compass? Can you still trust them? Well, maybe not. Maybe everything is blown out. And of course you can have a GPS in your oven in Faraday's cage, but the only story I have heard of that is that some nice guy wanted to bake bread for the captain, put on the oven in the morning, and well, it became a baked GPS. I also have a GPS, of course, hidden away in a metal case, but it's always good to have a second means of navigation, because GPS is maybe reliable, but how about if there's a warfare? How about all these GPS jammers are being used now? You can buy them really inexpensively on the internet. These GPS jammers, these small ones, really cheap ones, they are intended to be put in your car. So the car doesn't transmit your position. Apparently, there are some good reasons not to transmit your position. And there have happened quite a lot of accidents with that. The worst one being I know of in Norway, where a small girl needed to be rescued by a helicopter. She got sick somewhere. So the helicopter should be landing on a big parking field close to where the girl should be picked up. But everything got blacked out from in the helicopter when it was landing, because all the trucks parking in the parking lot had each a GPS jammer to hide the fact that they were parked there and not driving around, I suppose. In any case, the GPS and navigation system were just blacked out by this in this helicopter. Well, these are maybe horror stories, but it is good to have a backup system on board. So this, with the GPS, you always need some sort of batteries, even if you have a second or third one in your mobile phone. And if the power system is blocked out because of lightning strike or some other problem, it's good to have a second mean of navigation. With a sextant, you don't need any power at all. And it's also good to verify your electronics by using the sextant, just to check if the electronics are still showing the right thing. I think you should use it regularly. Why I love doing it is because of tradition. I mean, to me, GPS is actually quite new. I mean, I sailed a lot before the GPSs were readily available on various boats and small sailing yachts. And I love it. It's a beautiful mechanical piece of equipment, like a mechanical watch. And I think it's something to inherit. If you haven't inherited a sextant from your own father or grandfather or grandmother or mother, maybe it's a good idea to get one so you can pass it on to your own children. And to me, it's a feeling of freedom. It's style and cool, and well, the vinyl is back. It's really a bit in to go a bit retro. And it's fun. I mean, if you have learned so much about sailing, this is just one step further on. It's quite easy to use. And the nice thing is, it's so deep, so you can go on and dig and dig and dig further in. It's wonderful to read the stars, to read the sky, to find your way by just looking around you and observing what's is readily visible. And for me, it's quite romantic. Picture yourself on the blue planet, somewhere, by just looking up into the sky. So in this short video, or short course, I will explain hands-on how to use the sun-run sun. And that has been done all the time before the GPS was invented by loads of thousands of cruisers and sailors around the world. So the aim of this course is not to give a complete picture. It's just to encourage you to start use your sextant. Use your sextant as a backup and get inspired. Maybe you want to learn more and participate on an RYA Yachtmaster Ocean Course, or go the whole video course that I have also placed on my homepage. And the aim is, of course, to have fun while you're on your boat. So to make things simple in the sun-run sun, I have put some conditions. So I have said that what you do is that you shoot the lower limb of the sun. I'm coming back to that throughout the course, but that means that you are only looking at the lower side of the sun that you place onto the horizon when you use the sextant. In very rare conditions, you could also shoot the upper limb of the sun. I have also said that you only use the sun and shoot it twice the day. So you shoot first the sun, and then you wait 2-3 hours, and then you shoot the sun again. That's what this is all about. I have also put the conditions that you are on the northern hemisphere, you are on western longitude, and it's summer, because that's what it normally is. Because when you are sailing in the Baltic, which is eastern, or North Sea, which is eastern longitudes, you would most probably not use the sextant. And for the rest, if you don't fulfill these conditions, well, that's the next step. Then just join the full course and learn everything that you can do, shooting the moon and the planets and the stars. And let's pretend you're on the southern hemisphere, or you're sailing on the eastern longitudes, or in winter, for that sake, like in the tropics. So here comes the little idea, the summary, how this all works. So let's assume that we are in western longitudes, it's summer, and you sail from Portugal to the Azores out in the Atlantic. So what you do is that you wait for the sun in the morning and you shoot the sun. And the sun is then east of us, and the yellow line is the azimuth. That's the direction of the sun, so it points a bit east to us. Actually, as you can see, southeast. You shoot with the sextant, and what you get is the first position line. That is very important, because in celestial navigation you never get a position right away, you only get a position line. So that means that you know that you are somewhere along that line, but you don't know exactly where. That's your first shot, that you know that you are on the brown line. Now wait 2-3 hours, or maybe more. The sun has moved on during the day. Let's assume it's due south of us. It's a good exceptional point in time, actually, because that is when we have ship's noon and the sun is exactly at its highest, which I will explain in a minute, and the sun is due south. While the sun has moved on westbound, we have also moved, because we are on our way to the Azores, aren't we? So we have sailed on a course over ground and a distance. So we have to judge our course over ground. Don't read it off the GPS, of course, but that means that you have a heading on the compass, you take the variation and deviation into account, and you try to also estimate the currents that are here in the ocean, and then you get an EP, an estimated position somewhere. So that means that you have traveled along a course and you have made a certain distance, and then you get a new estimated position. So that means that we have moved along this line from morning to noon, and that means that this position line also has to be moved in parallel to a new position. So then we have a transferred position line. So this is the morning shot moved or transferred to the time of ship's noon. So now it's ship's noon, so we shoot the sun a second time and get a second position line. So we know now that somewhere along position line number 1 and somewhere along position line number 2 is our fix. So where is it? Well, it's here, isn't it? So our estimated position was not quite wrong. We have to move our little boat a bit to get to our fix. Of course, you don't have to do it at noon. It's just a simple thing to do, which I will explain later in the short course. So if you miss noon, or maybe it's the sun is in the clouds, or you want to have a third possibility, then just wait a little bit longer until it gets afternoon. Get it again, the sun shot, the direction of the sun, and get a third position line. Now, in this example, we haven't moved the boat, but of course you needed to transfer the first fix. So this is how you do. You get position lines, and where they intercept, that is where your fix is. Now, we're using stars and planets, and look at this. This is the sun that we have here, and we have all the other planets, and we are on that little planet here, the Earth, and all the stars around us. And isn't it fantastic? On this minuscule little blue planet in the universe, we look up into the sky and we can determine where we are on our little ball. I mean, just this is fantastic. And just the idea is worth examining how to use the sextant. So what is a sextant? Well, the whole thing is all about angles and time. So that, I think, is very important. We have time and angles. That's what we are all playing with. So the sextant itself is an angle measurement instrument. So what it does is that you take a celestial object, here we talk about the sun, and it is being reflected twice via two mirrors. It goes to the eye via these two mirrors. At the same time, the lower mirror, the horizon mirror, that's semi-transparent because the horizon is going straight through. So when you see the sun and the horizon at the same time, then you can read off the angle between the sun and the horizon. So the angle is measured down here, as you can see there where the arrow is on the sextant. In many courses, you talk about the celestial sphere. And to me, I think it's simpler to do it a bit differently. What the celestial sphere is, I wish to mention that we are pre-Galileo and pre-Copernicus. So what we in celestial navigation believe is that the Earth is standing still and all the stars and suns are hanging somehow on a ball, on a celestial sphere around us. And then we position the stars and the planets and the sun and everything in relationship to us, namely in relationship to the center of the Earth. So look here, we have a line here that goes from the center of the Earth out onto the celestial sphere, and by this line we define the position of the various objects in the sky. So I look at that now on the Earth. So here again, this is the line pointing out into the universe, onto the celestial sphere where all the suns and stars are based. Now, this is a line, and you can have another line close to it. So let me put another line here. So this is, for instance, 1 degree between those lines. And you can see that the distance between those two lines increase the further out you get into the universe. So in the center of the Earth, the distance between those two lines is, of course, 0. But the further out you get, the bigger gets the distance between those two lines. And on the surface of the Earth, That's where we live. That's where we are interested to translate this degree into a distance. So we'll zoom in here. So we translate this 1 degree into a distance. So 1 degree is divided into 60 minutes on the arc. So that is a definition that you take a degree and you divide it into 60 pieces, and then you have a 60th of a degree. So from that line to that line we have 60 parts of a degree, 60 minutes. Now on the surface of the Earth, where we live and where we sail, this is defined as 60 nautical miles. I don't know if you knew that, but a nautical mile is a 60th of a degree of a great circle on the surface of the Earth. And this is very, very important, because suddenly we can have an angle from the center of the Earth out in the universe, translate it into a distance on the surface. So angle and distance is the same thing. It can be translated into each other on the surface of the Earth. Of course, out in the universe, the distance is longer. Down in the center of the Earth, it becomes even 0. But on the surface, that's the only thing that we are interested in. 1 degree is 60 nautical miles. Okay, so it has to do with measuring distances. So how do you measure distances? Well, if you have one point and another point and a ruler, and you want to know the distance between those 2 points, and you're not allowed to touch the ruler, not to move the ruler, then there's a very simple trick. You measure with a divider. You take the distance here, you move it here to the ruler, and you say, for instance, the distance between those 2 points is 7.5 centimeters. Okay, that's what you do on the chart as well, isn't it? So look at the chart now. If you take the chart, the ruler is always on the side here. The ruler you may use is only valid on a great circle. That is the longitude. That's why measurements is always done along a longitude, along the left side or the right side of the chart. So let's assume we are here in Shetland and we want to know the distance to Bergen. And there's a coconut tree there. I know there are no coconut trees in Bergen, but let's assume there is something, a nice tree there, and we want to know the distance. So we take our divider here, and then we go and measure over here, and we see this is 180 miles. Now, can we translate these 180 miles into degrees from the center of the Earth? Yes, we can, because they are related. So if we see the center of the Earth over here and the chart on the surface, then we can say that the 180 nautical miles corresponds to 3 degrees, because every degree is 60 nautical miles, and 3 of these are 180 nautical miles. So that's the idea, that if we had a sextant in the center of the Earth, then one could measure from the center of the Earth 3 degrees, we could immediately translate this into a distance. Well, that's nice. So let's look now on our planet. We have our boat here, we have the palm tree there, and we have the center of the Earth over here. So if we just could measure the angle taken from the center of the Earth, we know how far we are from the palm tree. Now, how can we solve this problem? That's the issue with celestial navigation, because it's an angle measurement instrument, the sextant. Okay, let's see if we can have some contact with the devil down in the center of the Earth. So we'll call him down there and say, "Hi devil, would you be so kind and measure this distance?" And he could then telephone it up to us. That would be great. But that's not how it works. We need to measure it from our boat. There is no devil, we have nobody to talk to in the center of the Earth. But the thinking goes that way. So how can we measure this angle that the devil would at our position in our boat? So follow me on this thinking. We're going to lift up the palm tree and grow it higher up in the sky. Still the same thing, right? The palm tree and the angle, no difference in the problem. Okay, let's grow it even bigger and put it on a celestial sphere and put the sun over there. And now comes the trick that I have said, that I don't like the celestial sphere. It's too far away and I don't understand it so well. So it's much, much easier to put everything on the center of the Earth, because it has all to do with angles anyway. So we take the star and look, where does the beam of the star touch or go through the surface of the Earth in the right angle on its way to the center of the Earth. This little sun there on the center of the Earth, I call it the picture point of the sun. So still, it's the same issue. It's just the roots of the palm tree, whereof the star in the top is the coconut of the palm tree. But it's still the same issue. If we knew the angle, we could then get the distance. And the distance is what we want to do, to get. So here, this is the distance in nautical miles. And now comes the important distance. This important distance is between us and the sun. And that's all what this course is about. The whole celestial navigation is about the distance between us and the picture point of the sun. This yellow distance, that is called zenith distance, ZD, or in American ZD. The zenith distance. The zenith distance can be expressed in degrees or in nautical miles. It's the distance between us and the sun. Okay, haven't solved the problem yet, have we? But we at least know what we want to know. The zenith distance. We shoot up the sun very far up into the sky. It is very far away anyway. So now we can see that this beam and the next beam shining through us, they are parallel. It's so far away that the two beams coming from the sun are in parallel. So when they are in parallel, the further away the object, the more parallel they are. So the moon, by the way, is very close. That's why you have a big problem there with the moon, because they're not parallel at all. But for the sun, they are almost parallel. If we now take a dotted line just above us, then we can see that we have the zenith distance above us. So what we now could do, we could lie on deck and look in the prolonging, take the mast and see how it prolongs up into the sky, and then measure the distance between the sun and this mast that points further up. Well, the mast moves to and fro. This wasn't a good idea either. But we are getting closer. Because what we can measure, that's not the sun's beam in relationship to a point exactly above us, but the sun's beam compared to the horizon. And since the point exactly above us and the horizon have an angle of 90 degrees, well, what we measure in orange here with a sextant is an angle which is 90 degrees minus ZD. And that angle that we measure here, it's called HO. It's the altitude, the observed altitude of the sun. So when we take the sextant and measure and put the sun on top of the horizon and measure the angle, we measure, after some corrections, the HO, which is nothing but 90 degrees minus ZD. Okay, so we have this then, and then we can just change the order and write that ZD is 90 degrees minus HO. That's the same thing. So all you do is you measure the object, you get the HO, you take 90 degrees minus the measured angle on the sextant, and we get the distance. We don't need the devil. So we get the zenith distance, the distance between us and the sun. That is really cool. So we'll measure the distance by angle. So how does it work? Well, let's assume the sun is here somewhere. Okay, so we measure the zenith distance. The zenith distance is the distance between us and the sun. So we know that the zenith distance here is the first one. We measure it in the morning, and we know that this is the distance to the sun. So we are along this first orange line somewhere. Then the sun moves on, doesn't it? So it moves westbound, and then in the afternoon we measure the sun again. The distance is now maybe different. I call it ZD2. And we are somewhere on the second circle. And where they intercept the two circles, here and there, one of these two places we are. Well, we would most probably know approximately where we are, maybe not on the southern latitude, maybe we are in the northern latitude, so then we know where we are. So that's the principle. So where these two circles meet, that's our position. But you need two shots, as you can see. So let's see how we can find our position. So we are here and the sun is there in the morning because it's east of us. So we shoot with the sextant, we measure the angle between the sun and the horizon, and we get the zenith distance simply by taking 90 degrees minus HO. And then the sun moves on, and we get a second distance, and we take 90 degrees minus HO in the afternoon, and where they intercept, that's where we are. That's the same thing shown in a different slide. We just have two problems. Well, zenith distance is a huge distance. So it's a huge distance. So that means that we need a chart which is so big that the picture point of the sun is on the chart and we are on the chart. But if we take such small scale chart, the thickness of the pencil is several miles, if not tens of miles thick. So that is not so practical. And the second thing is, in order to know where we are, we need to know where the sun is. Because if we find out the distance between the picture point of the sun and us, then if we want to draw it on a chart, we need to know the position of the sun. And both this can be solved. And that's what this course is about. We have one special case. That's a really cool case. Because let's start again. We are here and the sun is there and we measure the zenith distance, and that's 90 degrees minus HO. Okay, we have HO, we take 90 degrees minus our measured angle and we get the zenith distance. Now we know that we are somewhere on a right angle line, the position line here. So now let's see what happens slowly along the morning. So the sun is moving a little bit. We get another zenith distance. This zenith distance is smaller. Can you see it? The sun is closer to us. And to get this equation right, the altitude needs to be increased. So the sun is higher up in the sky when it is closer to us. Well, makes sense, doesn't it? Because the more we go towards midday, the higher the sun is above the horizon. And here comes the special case. That is when the sun is due south of us. So now the zenith distance is minimal. That's the shortest distance between us and the sun. That's why it's the warmest and in midday. And then that means also that the altitude is the highest. The sun is the highest over the horizon. What is so special about it? Well, the position line, the brown dotted line here, which is in right angle to the yellow direction of the sun, the azimuth, the yellow azimuth, that is a horizontal line. And a horizontal line, that is on the chart a latitude. So that means that if you do a sight exactly at noon, or more or less at noon, because the sun is actually quite a long time, about 10 to 20 minutes on its highest, then by getting your position line, you automatically get your latitude. So that's cool. Look at this. The latitude is the distance between the equator and yourself. Distance measured in miles or in degrees, as I said. So at 0 degrees, you are at the equator. And if the latitude is 90 degrees, you are on the North Pole. But here, your latitude is somewhere, I don't know, 40, 50 degrees. That's the white line. And the zenith distance you have just measured, that's good. So all you need to know is this little distance. That is the latitude of the sun. And because the celestial navigators are all a bit fancy and showing off a bit, they have special names. So instead of calling this the latitude of the sun, they call it the declination. So we need to know what is the declination, because if we know the latitude of the sun, the declination, then we know that the latitude is nothing else but the zenith distance, which we can measure by the sextant, plus the declination, at least in summer. And as I said, this short course is all about you sailing in summer. In winter it's very similar, but I don't want to get into it here. If you're interested, go the full course or join an ROA Ocean Yachtmaster Ocean Course. So this is called the noon sight. So now let's look at the noon sight from the side. So it's summer, so the sun has a northern declination. The sun has its latitude, its picture point on the sun, of the sun on the earth, is on the northern hemisphere. That's what we call summer, because if the sun is on the southern hemisphere, then we call it winter, as seen from the northern hemisphere. Of course, the Australians call that the summer. It's always if you and the sun are on the same hemisphere that you call it summer. And if they are on contrary hemispheres, that means that the sun is on the southern and you are on the northern hemisphere, or vice versa, you call it winter. So this is summer. So in summer, the latitude of the sun is on the northern hemisphere. The zenith distance, that's this, the distance between your boat and the sun. So the latitude is nothing else but you add these two together, zenith distance plus declination. So how do you do this? Well, look at that. I've shown it before. You shoot up the sun. These two beams are in parallel. You have the zenith distance here between the rays of the sun and a point exactly above you. That's not possible to measure, so you measure it instead in relationship to the horizon. So you take the 90 degrees minus zenith distance is the HO, and you can then easily calculate the zenith distance is 90 degrees minus HO. So the latitude is very easily obtained. So all you need to do is take 90 degrees minus HO plus the declination. I hope this is now clear after having explained it in several ways. It's only the problem is, what is the declination? Well, even coastal skippers can find the declination in the reeds. It's actually shown here a bit roughly, I must say, but it's by 1 degree accuracy. You can see in what period of the year the sun has which declination, and then you can interpolate a little bit. So by 1 degree you can even use only the reeds. A bit more precise, you use the nautical almanac. So if you look at the nautical almanac, then you get it more precisely, because it is printed for every day of the year and for every full hour of that specific day. So here, for instance, we have the 15th of June, and we can see here that it starts off with 00 hours and then 1, 2, 3, 4, 5 o'clock. It's all in UTC. We're only talking UTC. That's so practical. So all you have to have is a UTC chronometer on board, and then you can use the nautical almanac. Look at the chronometer and you know what is the declination. So what you do is you look here, for instance, there is the declination, and you can interpolate by eye between hours of declination to the full minute. So this is the trick, that you don't need to do very complicated things. So for instance, you can see on the 15th of June at 2 o'clock, you have a declination of north 23, don't forget this N23 on top there, north 23 degrees and 17.5 minutes north, and at 3 o'clock it's north 23, 17.6. So never mind these decimals after the minutes, after the 17, because the sight reduction table that we will be using later, they don't take these decimals into account anyway. So it's very easy to interpolate to the nearest full minute. So here I would say if I shot, for instance, at 2:30 or 2:40, I would say, well, it's somewhere between 23 degrees and 17.6 and 17.7. I would round it up to 23 degrees, 18 minutes. So that's all you need to know. So now you can go out actually and shoot the sun, and then do it at noon and see what your latitude is. My next chapter is about disturbances while measuring, because what you are reading off your sextants is actually not HO, unfortunately. It is called HS. That is what you read off the sextant. And you need to have the true observations. And that is because you have some disturbances between what you see and what you really have observed. That's why you need some corrections on your way from HS to HO. So what are these corrections? These corrections have a lot to do with the horizon. Well, the horizon can be different. So the horizon can be crispy, like here. That's very easy to see where the horizon is. The horizon can be misty. It's very difficult, if not impossible, to read off and decide where the horizon is. And it has to do with the semi-diameter. I'm just mentioning these points without going too deep into them, because you will see how easy you can deal with them in a minute. So semi-diameter issue is that what you do is you look through the sextant and you look for the sun. Where is the sun? And then you see here, and then you take it down. And what you should be doing is that you should really, ideally, measure the sun there. So when the center of the sun is exactly on the horizon. Now that's very difficult to determine. With a star and planet, that's not a problem at all. It's only a dot. So when the dot is on the horizon, that's where you measure. But in this case, the sun is a quite big round circle. So it's much easier to do it by putting the sun, lying it onto the horizon with its lower limb. So look at this. This is what you really want to measure, but this is what is much easier to measure, the lower limb. So then you swing it to and fro to make sure that you really have reached the correct angle. And then you measure, you read off the sextant, but you have to add a correction, because you are not measuring as much as it should be, because the sun is not really in the center. You could, as I mentioned, also measure the upper limb. And if you measure the upper limb, then you have to subtract the correction. So it depends on the lower or upper limb. But my short course here is all about shooting the lower limb, which is so much easier. What else do you have to take into consideration? Well, the height of the eye. So as you can remember from your other sailing experiences, is of course that depending on how high an object is, the higher the object is, the further you can see. And there's a nice formula how you can calculate how far the horizon is away. So that's the problem when you do celestial navigation, because let's assume you're on a boat here and you really want to measure the star in relationship to the horizon. So the horizon, you should actually be down on the water level and do this, but you are not. You are at deck level. So at deck level, the horizon is further away, and that means that you measure a bigger angle actually. And if you do it on a mast top, for instance, here the horizon is even further away because you can see much further. And that means that if you measure what you should be doing here in orange, that is the angle you should be measuring. But since you are on the deck here, you measure a bigger angle. And if you'd been even higher up on the mast top here, you would measure an even higher angle. So the angles are depending on the height of the eye. And this is called the dip. So this correction depends on the height of the eye. And it's always negative because you always measure something which is too big. then you might think that you have some problems with waves. But you can actually disregard from that, because if you are high up on a wave, well, then you have, let's assume the waves are the same, of course, if there's not a tsunami, at the horizon. So the horizon is also higher up. So if you measure like you would on the crest of the waves, on the top of the waves, then your horizon would be just as far away. So that's why you don't have to worry about the waves. But you need to worry about the refractions. Well, the refraction, that is a problem. The lower the sun is, the bigger the refraction is. The refraction means that the sun is not there where you think it is. It's actually just about to go down now, to disappear behind the horizon. But it looks as if it's rather high on this picture. That's why you should never shoot the sun or any other object when it's lower than 10 degrees. So the tip is always shoot anything where the angle is at least 10 degrees on the sextant. What is refraction? Well, go back in physics and you might remember that when you measure an angle, this is what you should measure. That's where you see the object, but you have the atmosphere in between. And as you can remember that if a light beam goes from one medium to another medium, it refracts, it got bent. So this is the atmosphere. So that means that we really see the sun here. That's where we think we see. So we measure the yellow one, the yellow angle, but the sun is in reality where it was in the previous slide. So you have to deduct something there. And it's always negative because you measure something too big. And the more the sun is exactly above you, the less is the refraction. So the lower the sun, the worse it gets. Look at this picture. The sun has disappeared ages ago. It's behind the horizon. So how do you know when the sunset is? Well, you don't need to know, but it's maybe nice to know. Well, this is sunset. So if the sun is half a diameter above the horizon, that is when it is setting. It's just nice to know how big the refraction actually is. And then you have the problem, are the beams really parallel? Well, that's what I said, that they are when they are really far away. But when they are closer to us than the stars, you do have a little thing to consider here. Because anything in the solar system does have a, albeit small, parallax. But the moon, which is around us, that's why it's very difficult to use, has a huge parallax. So it's only in the solar system we have this problem. So let me sum up. Which problems do we have? Well, we have the disturbances of the index error, which I haven't mentioned yet, but that has something to do with the fact that the sextant is not showing the right angle. That's a sextant problem, but that can be eliminated by just checking it. And in the practical part later on, we will see how easy it is to consider the index error. Then, as a second thing, we had the dip, which had to do with the height of the eye. So we have that to consider. And then we have the problem number 3, that is the refraction, that the sun actually isn't there where you think it is. And for the sun, it's about 6 minutes, the refractions, under 6 minutes, up to 6 minutes. 6 minutes, 6 nautical miles, remember? So that is quite a lot. So we have to take that into consideration. And then we have the semi-diameter of the sun. We should really measure the center of the sun, but what we do is either measuring the lower limb, which is the normal, or maybe also the upper limb. And here, the semi-diameter of the sun is 16 minutes. That's quite a lot. That's 16 nautical miles. And for stars and planets, well, it's a dot already, so that's nothing. And last, but not least, for the moon at least, we have the parallax, that the beams are not in parallel. And if you want to know what parallax is, just take one finger, hold it in front of your eyes, and then close one eye and see how the object behind the finger seems to move if you look with the left or right eye. And the parallax is bigger the closer the body is, to you. So with the sun, it's really hardly worth mentioning. It's 0.1 minute only. That's a cable length worth of error. But with the moon, it's up to 1 degree, so that's actually 60 nautical miles. Okay, so how do you take all this into consideration? How do you do that? Well, in the long course, in the big course, there I actually go through all these points. But there is a good shortcut, and that's my template that I have developed. And I have been doing this. This is the template. So here you can sum up the corrections. And these are valid for if you are on the at about 2.5 or 2.8 meters above the water level, and then it sums up all the errors. So all you do is what have you measured on the sextant, and then you interpolate here and add a certain number of minutes, and it's all built into the same error. So that's very practical. Of course, it's not as accurate as if you go the long way, which you have to do if you do the Yachtmaster Ocean, but the error is no more than 0.3 minutes. So that's just a third of a nautical mile, so that's not much. So if you're in a hurry, or if you just want to make it simple, well, go for these template things. What else can we consider? Well, you can, of course, have some shaky hands. It's not so easy in the beginning to shoot the sun, but after some, well, it's only if you've done half a dozen or a dozen of shots, you really get used to it and you become very good at shooting. It's not as difficult as one can think. My tip I would give is that on a clear day, shoot from as high up as possible. You have to take into consideration, of course, your height of eye. In haze, then you want to go under the haze, so shoot as low as possible, and then take several shots and check the best one on the line. How do you do that? Well, it's fun. You don't even have to do any sight reduction or any calculations. Just take a piece of paper and draw two axes. One is the time axis. Here's the time, and here are the altitudes, the angles that you measure off the sextant. You don't have to do any corrections at all. Just note down what what you read off the sextant. And my tip is that it approximately works quite well if you do that within, say, 6 minutes, that you take one box as 10 seconds, because then you have 6 boxes, and that is 1 time minute. So if it is, for instance, in this example, I don't know, 15 hours and 14 minutes, 15 minutes, 16 minutes, 17 minutes, you can write down the time here, and then you take the different angles. Of course, you take the smallest and the biggest angle, but it is quite practical to do one box as 1 minute on the sextant. So if you read off 50 or 55 and then 00, that's a full degree, and then you continue 5 minutes and 10 minutes on the sextant. So every box is a minute. And when you've done this, you just draw in your different shots. So for instance, at 14 minutes and 15 seconds past the hour, I shot this one, and I shot this one, and then I shot one here down there at 16 minutes and 15 seconds down there. And you can see that when you connect these in a line, that maybe there is some that is out of line here. This is the third shot you should maybe not take. And then you pick one which seems to be the most accurate. And my tip, another tip, is that to get the angles and the times, is that if you are on the sextant, then have a friend, a buddy, to take the time with the chronometer or your little hand clock or watch that you have calibrated, of course. There is a video on how to calibrate your watch on my website. And then write down, have your friend writing down first the seconds, because they move the fastest, then the minutes to the left, and then the hour to the further left. So in the end you have hours, minutes, seconds, but you start off by making a note of the seconds because they move so fast. When it comes to the hour, check that you are in UTC. That's very important, that you are not in some sort of ship's time or local time, or what your smartphone has set your time on.
Yes, and last but not least, the horizon can give some distractions. So it's not easy always to look at the horizon and the sun, because there's a lot going on maybe on your side of the horizon.